Hello, this is lecture number 4 of this series of mechanism analysis or linkage analysis and design. And we're talking in this lecture about the position analysis of linkages. And I just wanted to say that normally when you analyze a linkage, you do either kinematic analysis or dynamic analysis, one of two things. So normally the analysis done or performed linkages would either be kinematic analysis or dynamic analysis. Kinematic analysis or dynamic analysis. Okay, so the kinematic analysis is concerned more with the geometry of motion, right? So how the motion is performed, with the rotary sliding, how the links are connected together, what sort of constraints are applied, and when we do that, we think of the linkage as being rigid, so the length of a link is not going to change during the motion. I think, and then we deal with the motion and geometry away from the forces acting on it, irrespective of the force. And like every link is compelled to move in a specific path by the geometry type thing. All right, so usually we spoke about degrees of freedom before, and one of the definitions of degrees of freedom is the number of parameters you need to define the locations of different points and links in a linkage type thing. And usually, like for a single degree of freedom linkage, you need one parameter, can be the angle of the crank, for example. If you know this angle, then you can work out the position of any other link in the linkage at this point in time type thing. So work out the position, right? So this is the first stage of kinematic analysis, and that's the position analysis. So, right, position analysis. Of course, this is geometry based 100%. And then if you know the position, you can go ahead and perform a velocity analysis. And if you know the velocity, you can then undertake the acceleration analysis. So those together are referred to, the three of them together. They are the kinematic, and they are the kinematic analysis type thing, right? So, right, it's in, right. So they are together the kinematic analysis. All right. Now with this together are the kinematic analysis. The dynamic analysis, when you do that, you'll be calculating the forces acting in links, right? And on the ground, right? Of the mechanism, because the links acting on the ground of the mechanism, like the bearings, if you like, the points of contact between the ground and the linkage, those forces are not constant in value. The forces will change with the position of the linkage, all right? So those forces are not constant. So they are, because not constant, they change in direction, they change in value. So you'll find these forces will be actually shaking the ground of the mechanism and hence causing vibration. So normally we refer to these forces transmitted to the ground as the shaking forces. And if we want to calculate the process of calculating these forces at different positions, of course, the acceleration also will contribute to these forces. The process of calculating the forces at different positions is referred to as a dynamic analysis. All right. So at this stage, we are looking at the position analysis of linkages. All right, okay. Now, I just wanted to say initially that the position analysis of linkage can be conducted, and possibly I have been doing this like a bit in the previous lectures, graphically, right? So just using the intersection of circles and lines and so on. And so, I mean, we can do that. So we can conduct, possibly I can just do some classification here. So I can say position analysis, all right? I can say position analysis can be conducted, you see, can be conducted graphically, as can also the velocity and acceleration analysis, by the way, and can be conducted also analytically, right? So graphically, normal would be done at one given at a given position or a value of a given value of the degree of freedom. But here will you obtain with this one, you obtain math formulas, right? You obtain mathematical formulas, and those formulas will be function of the degree of freedom of the linkage, right? So this will be a function of the degree of freedom of the linkage, all right? We are going to do both, but most of what we are going to do would be more analytical. So our focus will be more here. This is our focus. We'll just introduce a little bit of of here, but the focus will be the analytical. We'll try to obtain equations. There is also another method, which is, you can call it computational, right? Okay, you can call this computational. Computational. All right. With this one, you really solve the problem. You solve differential equations. You solve here. We solve the velocity equations to obtain positions. So this goes against the usual calculation. When we do position, then we differentiate to do velocity and so on. So you'll find it will be possibly more, will be easier to work out velocity equations for some linkages, and for those ones we work backwards from the velocity equations to calculate the position. So this is very much like integration type process, this one here, and we'll actually do some of that as well. So we'll look at this in the context of velocity analysis. We'll look at a little bit of that now, and we'll look at this also straight away once you've done the graphical solution. We'll start looking at the analytical solution. All right. All right, we can now start looking at possibly um, some graphical, just examples. All right, just a quick ones. So if we say, right here, if I go, that's an example here, and I have the slider crank linkage. So let's say okay, I'll try to insert a line here, or insert circle, see if this would work. And then let's say this is the crank here, right? So this would be the crank. And let's say I have, in fact, just flatten this here. I can flatten that as well. And I'll insert another line just to say this is my ground. So the ground here. So the ground, I think. And then I will have a connecting rod. So if my connecting rod is another line, so that's my con rod here, right? And there will be a slider at this end. So let's say we'll have a slider here, so that's con rod, be a slider. Then let's say we have a small slider acting here. All right. So in any case, those ones here. All right. So there becomes one thing with the page. All right. So let's say this is my, we call this, usually we refer to this as this specific linkage as slider crank linkage. This linkage here is a slider crank linkage, where this is the crank here and this is the slider, right? So normally the crank, there is some angle associated with that angle. Crank link is link number 2 usually, and this is link number 3. We refer to this as a con rod. Possibly that's a con rod here, link number 3, and then you get the slider as being link number 4 at this other end. Now, what if the crank changes position from this given value theta2 to another value? So let's say the crank becomes, instead of here, changes its position to another location. So if the crank instead of here now is here, right? So this is the new position of the crank, let's say. Now I want to find the new position of the slider as well, and possibly even the con rod as well. So I know now this point here, point A, would have moved to another position, A prime. So I want to find this point here, point B, would have moved to another point, which is B prime as well. And I want to find that. So let's say that the con rod has a length R3, the crank has a length R2. So it's obvious that if I draw a circle from this point here, point A, with a radius R3, this radius here, R3, it will of course intersect the ground at point B, right? So I can repeat the same thing at point A prime. So I can draw also a circle. Let's see if we can draw like a neater circle here. So, all right, so just get this here. Another color. So composability can, all right, I'll just try this one. So I'll try this color here. So let's say I draw a circle. So I want a circle. Okay. All right. So this will require some manipulation on my part a bit, just to make it look like a circle. Right. So here, let's say it's a circle length. The radius of the circle, let's say that's equal to R3, and the center of this circle is A, right? So circle is A prime type thing. So let's say this is the circle, the center of the circle. So I'll find that, assume this is the center of this circle here, right? So let's say the radius here is R3, right? So this circle will intersect the ground again at another point. This will be another point for the slider, right? So I'll try to draw a line here. So just possibly draw another line. So this one, insert a line. So I'll go to insert the shape and we'll get a line. So this will be a line which will go to the point of intersection, and this will be the new position of the slider. Okay. So this will be the new position for the slider, right? Okay. Now you'll find that, so once you have done that, you can find, you want to calculate, now at this point in time, you want to calculate this distance here, which will simply just be, this distance here will be just the distance traveled, the distance x. This is a new value of the distance x, right? So, or not the distance, not travel, it's the distance from point O2, which is the origin or the pivot of the crank, to the slider is the distance x, right? So, and I can just, so the x at any value, if you like, at any value of theta 2, that's how I get it. This is a new value. This is a new theta 2, and this would be given to me. So this value would be given to me. All right. Okay. Now you realize, so that once you have done that, you have actually solved the problem. And also one thing you can find and possibly be required at some point in time to calculate is the angle. So the crank angle or the angle of the connecting rod. So the connecting rod here has some angle phi, right? The angle changed maybe slightly to phi prime or something like that, right? Sort of thing. So, or maybe, you know, I mean, would have changed from one position to another. The maximum value of this angle phi obviously will happen when point A is vertical like that. This will give you maximum value. This will be as high as the con rod, which is link 3, can travel upwards. And when point A is on a vertical line downwards, this will be as low as the con rod can travel in terms of downwards type thing. So this angle phi here, you can measure it off the drawing as well, and you'll be able to measure x as well, which corresponds to a specific angle theta 2. Now, this, of course, has to be done to scale. So you can do it on AutoCAD or you can do it in paper using equipment and stuff like that, right? So to be able to have done graphical position analysis. And imagine this has had to be done for the whole, you want to find x, which corresponds to a whole range of theta from 0, for example, to 2 pi. So you want to find the values of x, right, on this curve here. And imagine you want to do this graphically. So you have possibly to move the crank 5 degrees and do the analysis every 5 degrees. It will be quite considerable and time consuming. That's why an equation would be better than this. However, an interesting observation I can now talk about based on my graphical solution, that I realized that this circle with the radius R3 has in fact intersected the ground link, which is this link here, at 2 points, not only one. So I have two possibilities for the slider. The slider can fall either at P prime here on the right hand side, or there is another possibility for the slider on the other side. Okay, now, so in fact, this other side here is the other possible way to assemble the same linkage. So you can tell now this linkage can be assembled with the slider on the right hand side or the left hand side of the crank, right? So that's another possibility. So the slider con rod can be here as well. So this is assembly number 2, if you like. All right. So on the right hand side, I have assembly number 1, and on the left hand side, I have assembly number 2. So right. So here this one. number 2, and this other one on the other side here is assembly number 1, right? So this is, so I have two different possibilities of assembling this linkage. Of course, in your machine, when you are, if you are designing something like that, you would just have one assembly and you do your analysis for the one assembly. And in fact, if this was like an given to you as an exam question or something, assignment or whatever, I wouldn't be looking for the other assembly unless I've been asked to. Normally, I don't have to draw the whole red circle here. I'll just draw a small circular arc, just enough to intersect the ground link on the right hand side. To just be to get a solution for the assembly I am dealing with, not for the two assemblies. I'm just like, what I'm doing right now is just to get you to think more, like in terms of broader terms, and you see a bigger picture than just what you would actually see. What would the assignments offer you? I want you to think as a designer and think in different direction and dimensions as well. That's why I talk about this other assembly as a possibility. Okay, now let's have a look at another example, possibly a four-body chain or something. All right, so yeah, this would here would have been X talking about. Now a four-body chain. All right, so I will go back to my circles and see if I can insert a nice circle to for the crank. So let's say this will be crank here, right? And I can just flatten this so it doesn't move around. I can have a line for the crank. So here I can just simply align from here. So this just to where the crank is located. Okay, just possibly just fix this with the page as well so it doesn't move around. And I'm going to have over here, just see if I change the thickness of this line. I want to have a line here just to represent my ground. So this will be the ground. Right, so let's say this will be the ground for me, and then I'm going to have as well, you remember the four-body chain, you would have like it's here. I have the four-body chain is something like that. Just drawing the side quickly, so it would be something like that. uh, it is something like that. So I have a ground, I have a crank, and I have link number 3, and I have link number 4. Link number 3, we refer to this as the coupler, and I would have on this other side, I'd have a rocker. So I'm just trying to draw those ones with circular arcs. So I would say possibly I would have this side here. I would change that. Okay. I would possibly have over here just another circle, and I will assume this circle would be the circle for the coupler. So the coupler would fall on this one. So the radius for this circle would be like R3 or something like that, and this will be the center of this circle. And I'm going to assume that I'll have also on this side here, I'll have R4, which is the rocker, and I'm going to insert a circle for the rocker as well. Okay, so I'll have a circle for the rocker as well. So if I have a rocker circle here, okay, so let's say this will be a circle for the rocker, and I'm just assuming now that, okay, so maybe like that, and so I'll just flatten this as well, this one here as well. So the two circles, just take them as those two circles. And here I'll have, this is the center of, I'll take this as the center for, this will be the center for like the rocker circle type thing. I'm going just to do this. And over here, I'll see the rocker would possibly intersect. If I take a line from here, and I'm taking this as my circle. So I'm saying my center. So I'll say this would be the point of intersection. This will be a point of intersection. Okay. So this will be a point of intersection. And then I can have also link number 3 from here. So this would be link number 3. So that's one possibility. So here I just matter of intersecting those circles again. So this will be R4 and this will be R3. So this will give me a possible solution. So that's a possible solution here. And so if given the value of theta 2, the question would say for given theta 2, this will be R3, and this will be R4, find, so theta 2 is given, all dimensions would be given in a question or a design. For a given value of theta 2, can be whatever value, find the angle of theta 3 and the angle of theta, or the angle of link 3, theta 3, and the angle of link 4, theta 4. So you'd be, then you're being asked to calculate, to find those angles here, theta 4 and theta 3. All right. So just now, as simple as I've done it, you'd have just matter of intersecting the circles. So you draw the end of your crank, point A, right? And then from this end, you draw a circle with R3. And then from the pivot of the rocker, you draw another circle with R4. The two circles will intersect, and the intersection point will be point B if you like. If this was point E here, this was point A. All right, and then you measure, so you draw this to scale, and then you would measure the values of your angles theta 3 and theta 4. If also the position of point B is required, you just measure the position. So you have to do this to scale to be able to say I've done a graphical solution, right? So without that, the values you measured will not be accurate. Again, just to alert you to something designers need to be aware of, the fact that my two circles, the R3 and R4 circles, intersected at 2 points just suggests to me there is another solution, right? So there is another linkage. In fact, I can draw or another assembly for the same R2, like for the same position of and location of the crank. I have two possibilities for my linkage, and they are really two assemblies. I mean, the linkage does not jump from one assembly to another during the motion. This will depend on how you assemble the linkage with the same dimension, the same length of those links. You can just assemble them in two different ways at the start, but then during the motion, it will just remain this specific assembly with you. So if you want to look at the other assembly, if you like, okay, let's do this quickly. And just let's draw it quickly. All right, I'll just draw the other assembly. So I draw a straight line. So I need one straight line here for R. So this will be R3. We'll go to here. Right, this will be R3, and maybe another R4 would be that, right? So I have over here two assemblies, and I can say that's right. So now I can say this is assembly number one and the other one is assembly number two, right? So this can be assembly two and the other one's assembly one. Okay, assembly one. So both assemblies share the crank. So you need to be really aware on that. So both of them share the crank. So here, the same crank. You see, for both, it hasn't changed. But the crank and one assembly and the crank, same and another assembly. So I have, for the same assembly, I can have both two cranks. Graphical solutions can also give you this insight into the structure of the linkage and how many assemblies I may have and stuff like that. But also, you should be able to obtain the same information with equations, right? Type thing. Also, if I want to go back to this initial here, like my example number one, also I had the two assemblies for the same crank, this one crank here and the same crank on the other side. I have another assembly, right? So when you do work out assemblies for the same input link, you can have a couple of assemblies. That's what I'm trying to say here. Now, let's have a look at um, maybe another example without much discussions. Like, okay, let's see if I can show you another example here. All right, so this will be page number 3. If I input another, yeah, no, just maybe just insert a drawing from the ones I had earlier. So let me find one of those designs. Okay, maybe this one here. So if we insert this drawing here, right? So let's insert this drawing and do this as another example. So that's an example. So just flatten that so it doesn't move the page. I'm going to say I'm going to call this example 3 or something like that, because this was example 2, this was example 1. All right, okay. Okay, so in this case, now I have, that's a similar interesting situation. That's my crank, and I have, when you look at this linkage, in fact, when I look at it, I can break it into two different things. Like I can break it into that. I can break it into a slider crank linkage here. So whereby the crank drives the slider into that, which causes this link to swing. So this link swings, right? As it's, this link here is really the crank to this other assembly. So this here is the crank to another 4-body chain. So this here is a 4-body chain driven by this other linkage, which is a slider crank linkage. All right. Okay. So when I look at it, I just to get some insight into what you're doing, you need to think like that. So you can tell for a 4-body chain, this is the input link. Once I know the angle of this link, I should be able to find where every other link is, exactly like my previous 4-body chain here. So once I know the angle of the crank, because this is like the crank, I can, this one link here is like the crank of this 4-body chain, similar to this crank, the blue link. Once I know the angle of that, I can find the angle of any other linkage. So once I know the angle of here, I can find the angle of any other link. And to get this angle here, angle of this link, I need to work from this end of the linkage. All right, so let's say now I have, so this link here is going to this is the crank. which will run on a circular arc, right? So this will be, so if this was R2, is going to be R2 as well. All right, so there's a circle with the radius R2. The center is actually here. And then if I tell you that I'm going to change the angle of the crank, which is theta 2, this angle theta 2 is going to change. Now, if it was like 20 or whatever, I'm going to have this as, let's say, 60 or whatever value. So I'm going to change that so the crank will have a different location. So let's say the crank is now here. So this point B has now moved to B prime. So this is the information I have. So this, I'm giving you this angle, this is a new position of theta 2, and given numerically, find, so theta 2 is 60 degrees or 40 degrees or whatever value, find, draw the linkage at the new position, because draw this to scale, that's a graphical solution, and from this drawing, find the angles of different links. Now, B was here, now it is actually here, right? Where is the rest of that linkage, right? Well, if you think about it, you'll find that like all the time, point B, which is the end of the crank, and the pivot of this link here, right? They are always aligned. They are on the one straight line. So this is a big clue for me. So that's this, and that's it. That's it. So once I realize that, I just connect those 2 points with a straight line. So that's it. So this tells me that that's point C. And of course, once I've done the connection on this line, so this line here, the red line, corresponds to this line. Just use a different color. Corresponds to this line, but in the new position. Because the line has tilted, and this line rotates about the fixed pivot C. All right. So this is the new position of this line. So this line has moved. Now look something like that. Okay. What about point D? This is D here. I want to find the new position of point D. Now I know point D is going to fall on this line, correct? So it's quite possible you can call this line locus for point D, meaning that locus means, this word means point D is going to fall on this line. All right, so point D is going to fall on this line. This is the meaning of the word locus. All right, okay, so that this red line is a locus for point D. I need another locus. So where else point D is going to fall? Okay, now when I have another look, I can tell you that point D is going to be on a circular arc whose center is point C. So that's another locus for point D. So this is another locus for point D. I'm going to write it here. So this here is locus for D. Right? Okay. Now I can tell you that point D will have to fall 100% on the intersection of the two loci, if you like, locus, first locus and second locus for the same point. They intersect to give me the location of point D. So this is like locus plus locus. I think the sum is called loci, something like that. All right. So then the two loci will intersect to give me the new position of point D. So this is D prime here. Okay. So now I know my slider is going to fall that, right? And this is point D. All right. Now how about finding point E? So now I have point D. Now, okay, the distance DE, this distance here, is not changing. Of course, that's fixed. and this tells me that point E moves on a circular arc whose center is D, right? So, okay, I can apply this immediately and say I can draw a circular arc here, and the radius of this one, right? So the radius here is ED, and the center at this point here. Okay, so this here is a locus. So I'm using this word one more time here, locus of E. So I need to find another locus of E. All right. Okay, this should be simple enough because I know E moves at a constant distance from F, this end here. So I can draw a circular arc, right, where E always falls type thing. So that becomes straight away locus of E. So now I have to decide where point E is going to fall and the intersection. So this straight away, this now says I have my point E prime right here at the new position. So now I just connect those two here. This will give me the new position for AD, then like in a new orientation. And then I can just draw the line over here to give me where the rocker at the other end, EF, is going to be. So at this point in time, I have done my graphical solution, and just based on the one value of theta2 at this end, I could find where every point is, like in the linkage, as based on this motion, and hence it's really a single degree of freedom linkage, and that's why it's possible to do that. Now, another example, I'll just quickly, I'll put this here in front of you. All right, so if I say example number 4, and just say, okay, let me in here just copy one of those drawings. If I have, okay, let's say this one looks interesting. So if I copy this one here, and just flatten it, okay, and then I say 4, so this is this value here, this is my theta2, right? Then if theta2 is going to change to any other value, so if theta2 change to any other value, find where every point is. Okay, so if theta2 changes from, if theta2, I'll just write here, if theta2 is equal to, here it's like 60, let's say it's equal to 80 or 120 or something like that, right? Draw the linkage. Based on what we did above, can you think you can do it? All right. You can do it on AutoCAD, you think, or you can even sketch how it's done. All right, what I'm going to do is to possibly give you a few minutes to do it. So I'm going to, let's say, just count 2, 3 and pause the video and see if you'll be able to do it, and then come back and see how it's done. Or if you couldn't, we'll discuss why it was not possible to do. I'm going to say 1, 2, 3. I'll pause the video for a second. I'll give you the time to try and do it yourself. Now, was it possible to do this linkage, like just by just one value of theta2 given? Well, if it was not, the reason is this is not a single degree of freedom linkage. If you calculate the freedom, this one here, if we calculate degrees of freedom, it's here I have, let's do this together. I have link number 2. This whole thing is one link. Link number 3. This whole thing is link 3. And let's say 4 and 5 and 6 and 7 sliders. So n is equal to 7 revolute joints, and that's a revolute joint, another revolute joint, another revolute joint. That's yeah, that's the centers are all revolute joints because the angles changed. 3 revolute joints, fourth, fifth, and sixth. So I have R is equal to 6. I have 2 prismatic joints. So that's a prismatic joint, another prismatic joint. Then when I calculate my degrees of freedom, I have 3 times 6, which is 7 minus 1, right? Minus 2 times 6, minus 2 times 2. So now here that's 4, that's 16, and this here 18, so it is 2. So it's a 2 degree of freedom linkage, meaning that I have 2 motors or 2 actuators running it. It's not possible just to give you one value, theta 2, as I did, and ask you to draw the linkage again. You needed 2 values. You need to find positions of 2 actuators type thing. So like in this case, you would possibly assume if I want you to solve it, I'll give you the location of one of the sliders, because I would imagine one of the sliders will be driven by a linear actuator or something like that. If the one if in the center point had like a rotary motor attached to it. So I didn't give you enough info over here for you to be able to draw the linkage. So that's why you couldn't draw it, right? So the missing information would be one, like a slider position or position of another, if you like, actuator type thing. Okay, so that's an interesting situation I wanted you to have a look at. Now, if I want to, some of the examples or you'll be dealing with or some linkages are not the link is not just a straight line, it's more like a laminate, triangular shaped type thing. And then you just apply the same rules and try to find where those triangles are. Or possibly, if I can do another example here, uh, let me see, and this is a quick one. All right, so if I do get an image from my images here, if I get, for example, maybe I can get this file, this example here. That's a simple one. All right. So, all right. So let me if I can see if I can do this one. All right. So now, all right. So if I say now, so this is link number 2. So this is link 2 here, right? And possibly this is link number 3. This is link number 4. I have 5 and I have link number 6. How many degrees of freedom I have here? So let's make sure it's 1 or whatever. I don't know exactly how many. Let's count that. So we have 6 links, revolute joints. We have 1, 2, 3, 4, 5, 6 revolute joints, and I have one prismatic joint. So my degrees of freedom is equal to 3 times 5 minus 2 times 6 minus 2. So that's 1. So it's a single degree of freedom. That's all right. So in this case, I'll just give you the angle of the crank here. So this is driven by a motor, and I would say if this point, so I know this is going to rotate on a circular arc, right? And then I say to you, the new position of this link is whatever value. Let's say it is 25 or degrees or something like that, right? Over here. Find, so this point has moved from here to there. So what should we call it? If we call it, doesn't have a name. So if I call it G, so this is G prime, the new position. And then draw the linkage, the whole linkage, when G has moved to G prime, or when this angle theta 2 is 25 instead of whatever it was. So the difference between those examples and the other ones, I have laminas for the links, like for 2 and 3. So they are right, and it's because the link is rigid, so it's quite simple to solve the problem really. Like if I have point G here, I need to find this point. If I call it H, for example, so the new position of point H, correct? I can find from point G, by the way, and then once I find the new position of point H, I can draw the lamina again, which represents link number 2. Same thing, like for link number 3, once I have found the position of the slider, I can build the lamina or the triangle around it with also circular arcs intersecting, right? And then once I've done that, I'll be able to find the point at the other end. And let's say it is point, let's call it like U or something, right? This is point U. So where U is going to go, and then I can draw my lamina again, and then find the point in between, like say point V, at the new position, all with intersecting circles in this case, right? So if I now point G is here, it will be very simple to find point H because I know this side E and this other side GH, they are fixed in value. So I can just, with the compass placed at B, I can draw a circular arc to just show how it will be locus for point H if you like. As point H is going to fall on this circular arc all the time, exactly as G falls on the blue circular arc. Right. So once I do that, I know the distance GH. So for I know G prime 100%. Then with a circle whose radius is a distance GH, I can find point H on the red locus. So I can say, okay, so over here, with this center here, I can draw, all right, this will be another locus, right, for H, right, and the center of this circle, the green circle, is G prime, and then this will, and the radius is the distance GH, and this green circle intersects the red circle at some point. This is H prime. Right, so now I have my lamina one more time. So if I connect those together, this gives me the new position of my lamina. As simple as that. All right, this is the new position of the lamina. And I repeat the same thing on the other side. Once I have managed to find my new slider, my position of the new slider, which is point A prime or something like that. So just maybe use different color here and say, like from here, from this distance, I can draw, right? This is well, you can just call this R3 if you like. So this is R3. So this will be locus for A, and the other locus for A is this here, this line. This is locus for A. The two loci intersect here, and this becomes A prime. So now I have A prime and I have G prime. Both A and G fall on represent one side of this link 3 triangle or lamina, and because I know the lengths of the other sides, I can simply just with the circle, with two circles intersecting, find the new position of U type thing, and then will be U prime. And then I have, once I have H prime and U prime, I know the distance C, the distance D. I do more circles, no, two more circles will intersect to find the new, to help me find a new position for my point V. And hence I would have done my linkage at a new position. I've drawn it at a new position. I've done graphical analysis. That's slightly more involved than other ones. And if you like, well, possibly some of those examples are quite easy to do. And usually, like graphical analysis is not difficult. but not all linkages lend themselves to simple graphical analysis, such as this one or the ones above. Some linkages are quite convoluted in design and would require more effort than the average effort to be able to solve. We're not going to see many of those, but I'll give you an example which I don't want you to solve. I want you just to try and see how it is, like if you want to have a go, that's fine. But it is quite difficult, I'd imagine. But I don't want you to solve it. I like, I really it's will you not find anything like that in the assignments or the exam. But it's one of the things which I think a little bit more difficult than others. And I just want you to have it as a mental challenge more than anything. And if you could solve it, please drop me a line and let me know how you solved it. Okay, so this here is another example, which is extremely difficult, right? This is high degree of difficulty. I don't want you to do it like solve it, not required at this stage to solve something like that. But if you want to have a go as a mental challenge, that's fine. All right. So I would just maybe leave it at this stage, right? And possibly in the next lecture, we'll start talking about the analytical methods to solve position analysis of linkages. Just before I forget, I just really want to say here that's high degree of difficulty. So that's my opinion here. And it's how many degrees of freedom? I think it will be one. So F would still be one. However, it's not easy to solve. All right. Okay. Well, do as many examples as possible and look at the things we have on model and try to do some of those and and just get yourself familiarized where finding intersections and like drawing loci for different for points and find for how things intersect and this sort of stuff, and possibly looking at simple linkages, the possibility of having another assembly, a different assembly, or like just have some fun with really with examples you have a model at this stage. In the next lecture, we'll talk about the analytical methods for a position analysis. Till then, thank you and have fun. Bye for now.